Have you ever really stopped to think about what happens when you flip a switch or pull the trigger on a power tool? It seems simple, but there's a hidden, absolutely unbreakable law that's running the whole show. Today, we're going to pull back the curtain on the physics that truly powers our world. So let's take an electric drill. You plug it in, you pull the trigger, and it spins. Easy, right? But where did that electricity go? It didn't just become spin, no. It goes through this incredible transformation. And once you get your head around that process, you basically understand the secret behind almost every piece of modern tech. You see, this whole thing is governed by one fundamental rule, the big one, the law of conservation of energy. It just means you can't create energy out of thin air, and you can't make it disappear into nothing. All you can ever do is change its form. And that electricity from the wall? That's just the very first link in a really fascinating chain of events.
Okay, so if the energy is just changing form, how does it do it? Well, inside that drill, or any similar device, the energy follows a very clear three-step journey. Let's trace it, right from the plug all the way to the work getting done. It all starts, of course, in the electrical domain. That's the juice flowing through the wires. But then it has to pass through a magnetic field, and only after that does it pop out in the mechanical domain as actual physical motion, like that drill bit spinning. Now that middle step, the magnetic field, that is the real magic ingredient here.
Yeah, see, the key thing to get is that the magnetic field isn't just some passive stop along the way. As our source material says, it's an energy storage and transfer medium. You should think of it like a bridge or maybe a currency exchange. The electrical energy can't just become mechanical motion directly. It needs this magnetic middleman to hand off the energy and make the conversion happen.
Okay, so we've got our three steps, but how do we actually keep track of all that energy as it's zipping through the system? Well, there's an official rulebook for that, a single, beautiful equation that manages the whole flow. And the best way to think about it is like you're balancing a budget, an energy budget.
Before we even look at the fancy symbols, the idea is incredibly simple, just like your own finances. All the energy that comes in, your income, has to be accounted for. Some of it does useful work, that's your output. Some of it gets put aside for a moment, that's what's stored. And, well, some of it just gets eaten up by unavoidable expenses. That's what's lost.
And here it is, the official rulebook itself. The electrical energy you put in has to equal all the other parts combined. W-elec equals W-mech plus W-field plus W-loss. Now, I know it looks a little technical, but don't worry. It's just our budget analogy dressed up in the language of physics. Let's break down exactly what each piece of the puzzle is.
So, first up is W-elec, the electrical input. This is all the energy flowing into the system from the socket. In our budget analogy, this is your total paycheck. It's the full amount you have to work with before anything else happens.
Next, we have W-mech, the mechanical output. This is the whole reason you plug the thing in. It's the drill spinning, the fan turning, the car moving. This is the productive work you're actually getting done. It's the real value you get out of the entire system.
Then there's W-field. This is the energy that's being held for a moment in that magnetic field we talked about. Think of it like your cash on hand or the money in your checking account. It's not the final product, but it's essential energy that's in play, ready to be used or transferred at any moment. And finally, we have W-loss. This is the energy that gets siphoned off into other forms you didn't ask for, mostly heat. In our budget, these are the unavoidable expenses. Think taxes, fees, inflation. No matter how perfectly you plan, you can never ever get this number down to zero. This is where reality bites.
And you know, that loss term isn't just some minor detail. It's what separates a perfect machine on a whiteboard from a real one in your hand. In engineering, understanding these losses, well, that's everything. It's the real cost of doing business in the physical world.
And these losses come in a few different flavors. You've got copper losses, which is just heat from the electricity pushing through wires. That's why your phone charger gets warm. You have core losses inside the magnetic parts, and then you have good old-fashioned mechanical losses, like friction in the bearings and air resistance. It's basically all the heat, the humming, and the noise that your devices make.
This really shows it all, doesn't it? On the left, you have the textbook fantasy, a perfectly cool, quiet, lossless system where all your energy goes exactly where you want it. But on the right, that's our world, the real world, where you always have to add that pesky little term for losses. It might seem small, but accounting for that lost heat is the key to designing machines that actually work instead of just melting.
So why did we spend all this time on just one little equation? Because this isn't just some abstract theory. This single, elegant rule is the foundation. It's the blueprint that our entire technological world is built on.
I mean it. Every electric motor in a Tesla or a blender, every single generator that lights up our cities, every tiny little relay and actuator inside robots and airplanes, they are all designed, analyzed, and perfected using this exact energy balance principle. It's the universal instruction manual.
And when you boil it all down, it comes back to that one core idea. A quote from our source material really says it best. The energy balance equation is basically a promise. It's a guarantee that the universe's most fundamental law, the conservation of energy, is being followed at every single step. Nothing is ever really lost, it just changes its clothes.
And that leaves us with a really cool final thought. We know the rules of the game. They're all laid out in this one equation. We know exactly where the energy goes, and more importantly, we know exactly where it gets lost as heat and noise. So the great engineering puzzle of our time is how to shrink that lost term. So, where is the next huge breakthrough in efficiency hiding? Is it in some brand new material? A clever magnetic design? A frictionless bearing? That's the puzzle that engineers wake up and try to solve every single day. Thanks for joining us.